this class, we are going to discuss we're going to use as an initial reference different postulates, and from these postulates, we are going to combine these with different vector properties. And since the electric field and the magnetic field, they are vector quantities, they will all the vector properties will reflect the way how the electric and the magnetic field is going to behave. So for this reason, we have to start this course initially with some discussion regarding the properties of vectors. And now, before we go to the vector properties, we want to mention a few of these postulates. Whenever we discuss about the postulates, one of the most fundamental ones is the charge conservation. Okay, so we can have charge conservation, which is a quantity which is measured, we denote it as Q. It has units of Coulomb, and this quantity can be described as a charge density per unit volume. So we might often see a rho v, and this one is going to be described as the rate of change, so dq over d volume, and here the units is going to be Coulomb per meter cube. Okay, so this would be whenever the charge is distributed over some volume. Then the charge, it doesn't have always to be distributed over some volume. It can be distributed also across a surface area, which is this piece of paper. In that case, we can denote this one as rho surface area, and this would be described as dq over delta s, and the unit would be here Coulomb per meter squared. Then the charge, it can be distributed also across a wire, and the wire, we can measure the length of the wire using meters. In that case, we would have the charge densities per unit length, and this can be described as delta Q over delta L. And here, the unit that we write here, equivalent sign, would be Coulomb per meter. So we can see that the charge densities that we can use, they can have different units. Now, these delta V's that we describe here, these are, or delta S that we observe here, they are infinitesimally small quantities, but these infinitesimally small quantities, from the practical reasons, we are talking about something in the order of 1 micrometer, okay? Ni micrometer, 1 micrometer is going to be the random delta V that we discussed here. Because since these charges are distributed on, let's say, on physical objects, this delta volume does not go to 0, of course. It has to be some upper limit, and the reasonable limit would be the distance between two layers of atom in a material. The difference between a few, for example, we are going to see in the future that the charge on a conductor, it resides, it stays on the outer surface of a component or of a conductor. But when we say the surface, this surface does not have zero thickness. It has a few layers of the atomic structure of which is covering the material, and these few layers, we don't know how many they are, but let's call it 5 layers. Okay. So we have 5 layers of atom, which is going to constitute the outer surface area of an object. And these layers, these atoms, this is how they look like. Okay, and it's not something that you need to memorize, but these distances between these layers, which can be 5 of these. Okay, here we're talking about 5 times 10 to the power minus 10. Wait a second. 3 angstrom. Yeah, this is the order. So it is in the order of angstroms. So if you have like 10, you might assume like 10, or let's say 50 or 100. We might go into something like a few hundred of nanometers. This is some number which it's not. You don't have to worry too much for the moment. but you might this might be relevant in the future courses when we discuss topics such as skin depth of a certain material, which is defined as the distance that an electromagnetic wave can penetrate through a certain material. In principle, these numbers you might forget this for the moment, but one thing that you might keep in mind is the issue that since we're dealing with critical components, these don't converge too much into some very small epsilons. Now, this is how we can describe the charge density, and we can also have relevant quantities such as the current density. So this is charge density. We can have current density, which can be defined as delta I over delta S, and the unit of this one can be ampere per meter squared. We can also have the J, which can be described as the rate of change of the current as a function of length over dm. So this can have a unit of ampere per meter. Okay, so these are some relevant quantities that we're often going to see. And now, during all this course, we're going to deal with quantities which will belong. So we are going to have two fundamental let's say fields. One is the electric field, and the other one is magnetic field. Okay. Now, both of these two different fields, they have an intensity and flux. Okay. So intensity is here, and flux is here. The electric field intensity, this is denoted as the E, electric field E that we have seen since physics 2 and probably earlier stages of our education. And the electric field flux, it is denoted by D, which is the displacement vector. Then the magnetic field, we have the flux, which is denoted as V, and the magnetic field intensity, which is denoted as H. Okay? So this is electric field intensity, electric field flux, magnetic flux, magnetic intensity. So these are the relevant quantities that we are going to see. And these two, they are related through an epsilon zero, and these two are related through some mu zero. Epsilon zero, it is the permittivity, mu zero, it is the permeability. Now, and the relationship between these is that we just multiply, so I think we can directly multiply the E with permittivity, we get the D, and we multiply this intensity with mu, we get this flux. So simply we can say that D is equal permittivity times intensity, and the flux here is permeability times, again, intensity. Now, immediately after this discussion of these topics, we have to discuss, to talk about vector analysis, okay? And regarding vector analysis, here we can separate our discussion. We talk about vector algebra. This is vector algebra. Then we can talk about the orthogonal coordinate systems. Orthogonal coordinate system. And then finally, we talk about vector calculus. So this is what we're going to discuss in the next minutes. And when we talk about vector calculus, after we learn how we can represent vectors, how we can add and we can do the product with those, here we are going to define gradient. In fact, gradient is an operator which is applied onto scalar quantities, maze, and vectors, but we're going to talk about this one. We're going to talk about the divergence and the curve. Okay? Divergence and the curve. Okay? That's good. So let's start with vectors. So in principle, a vector, we have taken linear algebra, and the concepts that you learn in linear algebra are very useful. And regarding these, we can start simply by saying that any vector A, this can be described as 3i minus j plus 2k. Okay? So here we have a vector, and it is imperative, or it can be very useful if we describe the vectors in column form, not as a row form. This would be 3, minus 1, 2. And this vector, it can be described like this, and this is a vector which is 3 by 1, or this is also equivalent, you can write it like this, 3 minus 1, 2, transpose, it is the same thing. Now, this is, in this discussion today, I'm also including the closed terminology that we're going to follow here together. Then we can have another vector b, which can be denoted as minus I plus j minus 2k. Okay? Now, ijk, we denote the x-axis, the y-axis, and the z-axis. Okay, so this is what we denote with these. And this is denoted as minus 1, 1, minus 2. Okay, this is another vector. And regarding these vectors, we can add them together. So we can a plus b, this would be equal to, we can add like this, 3i minus j plus 2k, and ijk, they are the unit vectors along the x, y, and z. So this is simply plus minus I plus j minus 2k, and this is equal to the I plus i's, we get here 2i, 2 units along the x-axis, plus 0j, okay, plus 0j, and the final one, it is plus 0k, plus 0k. Okay, so here we obtained, apparently, that's what we ended up with. So the vector A, it is along the, it's in the 3-dimensional space. It's a vector which has a projection along the x, along the y, and along the z. B does the same, but the summation between these two vectors apparently is just along the x-axis. It has no projection along the j or along the k, or along the y and along the z. Similarly, this addition of these vectors, let's not forget that these are vectors, this can be denoted also as 3 minus 1, 2 plus minus 1, 1 minus 2. So this is the vector notation that we have seen in linear algebra. So here we follow the same. We have a vector which is 3 by 1. We can add with another vector which is 3 by 1. 3 minus 1 is 2. 0, 0. This is 3 by 1. That's good how we add these vectors. Now, these vectors, we can define dot product or inner product. So here we can denote this one A inner product with B. Okay, that's one way to represent this. Or we may have seen this one in a more common way. And the inner product, which can be represented here, this is also equal A times B times cosine theta. For a moment, allow me to use the language of linear algebra, which this one, which is denoted as inner product or dot product, this can be described as AB. This is equal to A transpose times B. Okay, A transpose times B, this is equal to what? What is A transpose? A transpose is 3 minus 1, 2. 3 minus 1, 2. Multiplied by B. B, it is minus 1, 1, minus 2. Minus 1, 1, minus 2. And this is a vector 1 by 3. This is a vector 3 by 1. So we know that when we multiply these two quantities, we should get, we should get the scalar quantity, okay? I believe you can see this now. And when we multiply these two together, we get minus 3, minus 1, minus 4, minus 4, minus 8. Is this correct? Let's check this again. Minus 3, minus 1, minus 4, minus 4, minus 8. Okay. That's what we obtain here. Now, this is purely vector notation. But now, what we can see from here is that A dot B is equal to the magnitude of A times magnitude of B times cosine theta. Now, let's think for a moment that we have I dot j. What is I dot j? This would be equal to the magnitude of I, and I, it is a unit vector, which means that it has a length equal to 1 times the magnitude of j times cosine 90. 90 is the angle between the x-axis and the y-axis, and here we end up having 1 times 1 times 0 equal to 0. So I times j is 0, and I times k is also equal to 0, the dot product, and the j dot k is also equal to 0. So this discussion that we are having here, we can call this one dot product or scalar product. Okay, this is a scalar product. So we take the dot product of these two quantities, and we get a number. We get a number which has only magnitude. Okay, and then we can also, so let's see actually what is A dot product B. A dot product B. This can be written as, let's see here, A, it is 3i minus j, 3i minus j plus 2k dot product with minus I plus j minus 2k, and this is equal to, and what we saw from what we see from here, we observe that here we can write 3i times minus I plus 3i times j plus 3i times minus 2k plus minus j. So maybe it's better if I should not forget that I plus minus j times j plus minus j times minus 2k. Then we have plus 2k is multiplies with minus I. Here we have j, here we have minus 2k. This whole thing, we know that the dot product between I and j, because this dot product is still there, this is 0, 0. J and I, this is 0. J and k, it's 0, because we have this. And similarly, this is 0 and this is 0. The only three surviving terms, it's this, this, and this. And as a result, we get here minus 3, minus 1, minus 4, this is equal to minus 8. So this is what we observe for the scalar product. Now, this minus 8, this would be equal, so this A dot product B, this can be, we can also define what is the magnitude of A. So for a moment, we can denote that the magnitude of the vector A is equal to the square root of the inner product of A with A, okay? And the magnitude of the vector B, it's the inner product of B with itself, similarly. And this would be equal to, we have here 3 minus 1, 2. So this is the square root of 3 minus 1, 2 times 3 minus 1, 2. This is the square root of this. And what we obtain from here, it's 3 squared is 9 plus 1, 10 plus 4 square root of 14. This is the magnitude of A. The magnitude of B, then it is going to be minus 1, 1, minus 2. Minus 1, 1, minus 2 times minus 1, 1, minus 2. And this is equal to 1 plus 1, 2 plus 4, 6. This is square root of 6. Then, from these two relationships, we can write this form here, which is equal to cosine theta. And then, from this expression, we can simply state that minus 8 is equal to square root of 14 times square root of 6 times cosine theta. Okay? And cosine theta, in this case, cosine theta would be equal to minus 8 divided by the square root of 84. 84, because 6 times 14, 60, 24, 84. That is correct. Here, we can also simplify this one a little further. This can be minus 8 times square root of 4 times square root of 21. Square root of 4 is equal to 2. This is going to be equal to minus 4 divided by the square root of 21. Okay? This is what we obtain here. Okay, so we can derive this information from the dot product between all of these vectors. Now, this dot product that we are doing here, this is defined for the Cartesian coordinate system, which is one of the possible orthogonal coordinate systems that we see here. Okay. So, all of them, we can write here, we have Cartesian, we have cylindrical, and spherical. So these are the three possible coordinate systems that we're going to see. But now we're still discussing about the vector algebra. So we did the addition, we did the inner product, the scalar product, or the dot product. Now we can talk about the cross product. Algebra. So we did addition, product, which is we did the scalar product, and the scalar product, it is denoted as A dot B. Now we find the vector product. The vector product, and we denote this one as A cross B. Now A cross B, at least in the Cartesian coordinate system, we denote it like this. So here we have A cross B, but first let's write this is going to be equal to some vector C. And the vector C, it is going to be such that C, it is perpendicular to A, okay, and C, it is perpendicular to B. Now, once we see this, this means that if A and B both define a plane, if we take the cross product between these two vectors, the result, it is going to be perpendicular to these two together, okay? And this is how we denote this one, and also regarding the magnitude, this will be equal to magnitude of C is equal to magnitude of A times the magnitude of B times sine theta, where sine theta is equal to the angle, or it corresponds to the angle between A and B. As an example, we can say here C, this is equal to, this is I, J, K. And A, we have to write A, it is 3 minus 1, 2. This is what vector A is, and vector B is minus 1, 1, minus 2. Minus 1, 1, minus 2. And then, from here, we have to determine that this is equal to I times minus 1, 2, minus 1, 2, 1, minus 2, minus J, 3, 2, minus 1, minus 2, minus 1, minus 2, plus K times 3 minus 1 minus 1, 1. 3 minus 1, minus 1, 1. And then C would be equal to the projection of C along the x-axis is going to be equal to, this is 2 minus 2, 0, minus j times minus 6, minus 6 plus 2 is minus 4. What did I say? Minus 4. Plus k, here we have 3 minus 1 is equal to 2. So C apparently is equal to 4j plus 2k. This is the C vector. And this is the cross product that we care for the moment. Now, okay, this is and then another important property that we should be aware of is that often we need to define so we need to define the position vector and the displacement vector. The position vector, it is so here we can have x, y, z, and let's assume that here at point P we have a charge, okay? So at point P, we have the charge, which is the source of some field that we can measure at point Q. Okay. So here we have point Q, and the charge is located at the distance R1, and the point Q, it is at the distance R2. Okay. So the point is like this: charge located at P, calculated field at point Q. Okay, this is how we can pose the problem. And in this case, we will be very much interested. So position vector, it can be described by R1 and R2. Okay. But then the question is, what is the difference, the distance between P and Q? This one will be defined as R2 minus R1, okay? So this is the displacement vector. Now, this is the origin. We can call this one origin O. And in this case, or often, we are going to see that a vector of interest PQ, this can be found as Q minus P, okay? Which means that, let's assume for a moment that the point P can be located at the coordinates, let's say 1, minus 2, 3. Okay, this is point P. And how can this be represented? This can be represented as R1 is equal to I minus 2j plus 3k. Now, point Q, where we want to conduct the measurement, I don't know what we can write about this, but we can advocate that this is a 0, 5, 2. Okay, this is where point Q is, and the position of this point Q, this can be written as R2. This is equal to 5j plus 2k. Okay, and then we want, so this is just a triplet of numbers which correctly defines these points with respect to the origin. Okay, then we need to find the displacement vector or the vector PQ, which in this case PQ should be equal to Q minus P, and this can be written as 0, 5, 2, minus 1, minus 2, 3. And this is equal to 0, minus 1, this is minus 1, 5, this is 7, 2, minus 3, minus 1. Okay? So, and in fact, this displacement vector, we can denote this one as vector D, which was equal to R1 minus R2. And this is also written as minus I plus 7J minus 1. Sorry, what is this? Minus K, right? Minus K. Okay, so now let's have a look. And we're dealing with these quantities. Now, often, an important parameter for useful notation will be, so we have, from the origin, we have a distance ρ2. But what is the direction of this R2? The direction of R2, it is along a unit vector, which we should denote it like this, okay? And the point P, it is a distance equal to the magnitude of R1 from the origin. But the direction, it has to be denoted by a unit length vector, which we can denote it like R1, okay? And here, this is the distance D, and this one is pointing along a direction, the unit vector D. So this is how we can denote these. So it is important to determine a unit vector along all the relevant distances that are important to us. So in this case, we can denote the unit length R1. This is equal to vector R1 divided by the magnitude of R1. And this R1 is equal to I minus 2j. Can someone calculate what is the magnitude of R1? Minus 2j plus 3k divided by what? What is the magnitude of R1? So this is the magnitude of R1 because we do the inner product of R1 with itself. We get 1 plus 4, 5 plus 9, 14. So the unit vector along R1 is it can be written as 1 divided by the square root of 14, I minus 2 over square root of 14j plus 3 over square root of 14k. Okay, so this is R1. Then, similarly, a unit, sorry, this is wrong. I apologize. It should be something like this. So the unit vector along R1 is this. The unit vector along R2 should be similarly R2 divided by R2. And what is the magnitude of R2? We should take the inner product of R2 with itself. So here we have 25 plus 4, it is 29. So here we're going to have 5 over square root of 29j plus 2 over square root of 29k. So these are the, let's say, the unit length along this specific direction. Now, I want to, the examples that we're providing right now should be very useful for you in the future chapters, or whenever we are discussing more general concepts, and that's the main objective why we're doing this. And I just want to remind you, for example, what was point P? Okay, an example. Point P was located, so we're done with this one. Okay? So we found how we express the position vectors, the displacement vectors, and all the relevant quantities. which are the unit lengths along specific directions. Now, for a moment, remember what we did, but let's come back. Let's have a look at this one. Apparently, a position vector, it is always described by the projection along the x-axis. Let's pick up this one, which is I. The projection along the y-axis, which is minus 2j, so it is minus 2 components along the negative direction of y, plus 3k, okay? Now, this is a specific case which counts for a location which can be described by 1, minus 2, 3, okay? But what could be the most general position for any point on the three-dimensional space? So let's consider, instead of the projection along the x-axis, let it be a value a, b, or let's call it x. Would you agree if we call that point x? So let that generalized point, let it be x. The projection along the y, let it be y, and the projection along the z, let it be z. Then the general position vector, it can be described as xi plus yj plus zk. Okay, so this is how we can describe the general position vector. Now, so this was all regarding vector algebra. So we discussed the products, the addition, subtraction, and we did here the position vector, displacement vector. And now, let's jump to the orthogonal coordinate systems. Now, regarding the orthogonal coordinate system, first of all, let's start with the Cartesian coordinate system. This became too long, okay, but anyway, Cartesian coordinate system. And the Cartesian coordinate system, it is described by and to use somewhere some part of the board which I'm not going to erase very often. So Cartesian, well, let's keep it like this. We use x, y, z, okay? And the unit vectors, maybe we are used to look at them as I, j, k, but this is also equivalent to anything which can be noted ax, ay, and az, okay? So then we're going to see two more coordinate systems, but let's get done with this one initially. So it looks like these are also base vectors. They are perpendicular, and the first thing that we need to define, we need to define the vector, okay? The length differential length, let me call this one shortly, differential length. And the third important component is the differential volume. So any vector in Cartesian coordinate system, it can be described as A. This is equal to AX times AX plus projection of A along the y in y plus projection of AZ. Now, this is exactly the same to like AX plus AYJ plus AZK. Okay, so they are all equivalent, but we're just writing using this notation because the textbook follows the same notation. Now, the next step that is essential to us is we should write a differential length. The differential length, it is the infinitesimal length scale in Cartesian coordinate system. Now, when we write the infinitesimal differential length, we should be including delta x, delta y, and delta z. Okay, so we have small steps that we can follow along the three orthogonal directions. So that this dl, this can be written as this is equal to, so this is a vector, this is ax dx, okay, plus ay dy plus az dz, okay. So with dx dz, dy dz, we are talking about the infinitesimal components. Then we need to determine the infinitesimally small differential volume. Now, the volume, it is a scalar quantity, and it should be equal to dx, dy, dz. Now here, I want to ask someone. You can raise your hand in the class option. Let me pick someone. Livia Muji. Or anyone can raise your hand. What is the unit of x? Someone can raise your hand in the option of raising the hand. Okay. Brandon?
Yes, Professor.
What is the unit of dx?
Meters?
That's correct. Okay, so this is meters, right?
Yes.
What about dy?
Meters also.
What about dz?
Meters too.
Volume?
Meters cubed.
That is correct. So let's have a bit, we have to look at this carefully because this is not always this easy. So, and also, similarly, we can observe that dl, it has units of meters, dx, it is units of meters, dy meters, dz meters. So we are good. It looks like when we write the differential length, we wrote it correctly. So we have meters plus meters plus meters. That should also be equal to meters. Also, regarding the differential volume, we have it in the correct way. Okay. Then, let's see, I think we calculated the unit vector. And we can see a small example here. So, if we have a vector A, which is equal to ax plus ay 2 minus az 3. So in this case, we could, so if this is the vector A, we can ask a question like this. Find the angle theta between A and z-axis. How can you find the angle theta between A and z-axis? We can do the following. A dot product with K, okay, or AZ, let's use our notation. This is equal to the magnitude of A times the magnitude of AZ times cosine theta. In this case, the A dot AZ, what is A dot AZ? This is just 3, right? Because what we can do is that we can do the product, dot product with AZ, like this. Okay? And the only non-zero term would be the inner product between AZ and AZ. That's what we get. And what is the magnitude of A? Magnitude of A, it will be, because A, let me use this part for a moment, A is equal to a projection which is going to look like this, 1, 2, minus 3. Okay? Then the magnitude of A, of vector A, is going to be 1 square plus 2 square plus minus 3 square root. It's like the Euclidean distance, okay? Which is 3 square, 9 plus 1/10 square root of 14. That's good. We got this. So then here it's going to be equal to square root of 14 times 1 times cosine theta. In this case, cosine theta is equal to minus 3 over the square root of 14. Okay, so this is 14. And another question that we can come up with is, let's wait a second, is the following. Let's assume this is A, and we have another vector, C. Another vector C, which is equal to 5ax times 5, ax times 5, minus az times 2, minus az times 2. Now, the question could be the following. What is the component of A in the direction of C? Time So, how can we find this? This is a good question. Well, to find this one, what we can do is that we can find the inner product of A, okay, with what? Let's think for a moment. What is the projection of A along X? The projection of A along X can be found using this. A dot product with AX. Okay, that's it. This is the projection of A along the X. And what we find is just 1. Then, what is the projection of A along Y? When we do this, we take the dot product of A with AY, what do we get? We get 2. And similarly, what is the projection of A along Z? We have to multiply, we have to find the inner product of A with a unit vector along the Z. What is this? It's AZ. So we do A dot AZ. And this will be equal to minus 3. Now, what is the component of A along C? This should be equal to vector A. We take the inner product with a unit vector which is along the C. Okay. So what is the unit vector along C? Let's write this one. Let's write it here. So unit vector along C is always equal to vector C divided by the magnitude of C. Okay. We did this one before, where we said we wrote this one, unit vector along R1, it was equal to R1 divided by the magnitude of R1. So what is C here? C, it is, and let's find the magnitude. The magnitude of C, this is equal to the square root of 5 square, okay, plus minus 2 square. So this is equal to, because these are the projection along the 2 orthogonal directions. 5 square, it is 25, plus 4, 29, is the square root of 29. That's good. Then let's go ahead here, and we have to write A. We have to calculate the inner product of A, which is 1, 2, minus 3, you can write it also this one like this. 1, 2, minus 3, dot product with what? C, it is 5, 0, minus 2. 5ax divided by square root of 29 plus 0 ay divided by the square root of 29 plus what is it? Minus 2 minus 2 az divided by the square root of 29. That is good. So here we just multiply these with 5 divided by square root of 29, 0, minus 2 over square root of 29, and here we get 5 over square root of 29, okay, plus 6 over square root of 29. And this is equal to 11 divided by the square root of 29, and this is the projection of A along the direction of C. Okay, so which means the following: we can have a vector A which has along the x-axis this projection, okay, which is this. But what if we have a vector C, which is shown here? This is A, this is C, and we may be interested into learning. Let's draw a perpendicular line. We want to find this. We want to find what is the projection of A onto C, and it is going to be this length. Okay? And all we need to identify correctly is this. Okay? So this was an example regarding what we can do in Cartesian coordinate system. Now we move to a different coordinate system, which will be the cylindrical one. The cylindrical coordinate system, let's write it here. By the way, cylindrical coordinate system, based on the meaning that it has, it is going to have a cylindrical symmetry. What is a cylindrical symmetry? Here we can show one. It is any construct that looks like this. Okay, and we need to identify any point on this cylinder. The points of this cylinder, they can be defined. Let's assume that here is the reference angle. We need to define a radius r, an angle phi, and the height z. This one, let's assume we have some point here. This point P, this has a projection on the xy plane. Okay? And this is the length r. This is an angle phi. Okay? And this is the height z. So point P, it can be defined by r, phi, and z. So apparently, we need to know how far it is from the z-axis, what is the angle with respect to the x-axis, and what is the height along the z-axis, or how far is it from the plane, xy plane. This is what we need here. So now, if point P needs a distance, an angle, and another distance, we need to define these variables, which are AR, okay, A phi, and AZ. Okay, and here, how can we determine Now, it's good to draw this one as good as possible. First of all, let's see what is the unit length. So let's try to, or let's do it in a second. No, we have to write down the vector. How does a vector look like in cylindrical coordinate systems? This would be written as follows. Vector A is equal to AR plus A5. What does this mean? This means that what is the projection along the A5 plus AZ. Okay. So, but now let's try to understand a little bit. Let's try also to understand: are these really orthogonal? So, AR. What is the direction of AR? Direction of AR, it is defined as the direction which is given when you go from point R to R plus dr. Okay. So what does this mean? This means the following. We have a cylinder. We are on the surface of the cylinder, and we are moving away from this point on the surface area. By how much? dr. Okay, so we are moving in this direction. What is happening? We are drawing a vector which is perpendicular. So apparently, what is the direction of AR? Direction of AR is right here. Okay. This is the direction of AR. Now, the other coordinate, it looks like the angle. So what is A5? What is the direction of A5? Then we say the following. See how much distance we are going to cover if we go from theta to theta plus d theta. Okay. Let's change the angle infinitesimally small. So here I have the cylinder, okay, and we are on the surface here. We are at this point, and we move by an infinitesimally small angle like this. So I'm trying to draw this one here. So apparently we care about this displacement. But this displacement, which corresponds to from an angle theta to an angle theta plus d theta, so I know this phi, sorry. This is phi, it's best if we keep the phi's here. This is phi plus d phi. So if we tie a string, if you tie a rope to the origin, and then we draw an arc, we move like this, right? We change the angle from phi to phi plus d phi. What is the direction of the line that we draw? The direction is going to be this. So this is the AR. Okay. I hope this is clear. But let's have another, maybe it is best if we show only the x and y projection here. Let's do that. So this is x and y. And the z, it is extending out of the board. And let's pick an initial direction here. We are at this point. What is AR here? AR is right here, okay? As a unit vector. Now, if we change the angle from phi to plus delta phi, let's increase this one infinitesimally small, that is much. From which point to which point did we travel? We travel along this, okay? So this means that a change of the angle by this much can draw a line which can be described as, this is the A phi here, okay? That's good. Now, let's assume we are at this point here. And then, what is AR here at this point? AR is this. This is AR. So it looks like AR in a cylindrical coordinate system, it is changing the direction as a function of the angle. And then, let's change this angle, which is here, Let's change by some infinitesimal small delta phi, and let's come to this point, okay? So, what is the path that we're going to draw? Is this. How did this happen? Only by changing the angle phi. So, apparently, this is the A phi, okay? Now, what is essential for us is the following. As we keep the radius the same, this is going to be perpendicular. This is going to be perpendicular. So AR and A phi, they are always perpendicular with respect to each other, which means also the following. AR dot A phi is something equal to 0. Okay? So you can keep this in mind regarding how the unit vectors in cylindrical coordinate systems behave. Now this was good, so we wrote this one in a good way. Now we need to write the next step. We need to write the DL. Okay. Now let's use our intuition. Let's not jump too much further. But if we want to describe the differential length, what is a differential length? You have an object that is located in one point in space, and you want to move it around, but by having small steps. And where are these small steps going to happen? It's going to be delta r, okay, delta phi, and it might be also a motion from z to z plus delta z, okay. So this is, so it looks like the differential length, the small length dl, it should be written something like, it should include the delta r, okay. It should include the delta phi, and it should include also delta z, okay. This is what we do. And delta r, this should be along AR. This one plus, this should be along A phi, and this should be along AZ. Okay? So the differential length, it is intuitive, okay? Even you can derive it. It is easy to derive. When we come to the exam, you don't need to memorize or derive these because we're going to have also spherical coordinate systems. You can bring a formula sheet or a cheat sheet. It's okay. But at this stage that we are deriving these, it looks like they should be intuitive. So we said that if we have r phi z, the direction of r is ar, a phi, az. So this is a vector. So the displacement can be described as a little motion along the dr, a little motion, a small change in the angle, a small change in the z. That's it. But now I want to ask Brendan again. Brendan, what is the unit of delta r here?
Meters.
That's correct. What is the unit here?
I don't think that radians.
That's correct. That's the radians. Yeah. What is the unit here?
Meters.
Meters, and this is also meters. Do we have a problem here?
Yes, because the two sides don't match.
That's correct. So it's a problem. We have to be a little intuitive here. So what should we do in order to write these lengths correctly? Now, so apparently we have a problem here. So when we move to polar coordinates, since we're going to use angles, we have to be a little careful when we define, starting from here, from the differential method. Everything is right on the road here. It is, everything we're reading so far, it's intuitive, no need to memorize, but we're missing something. So now, an infinitesimally small change along the r, it is delta r. But what should be, what is this length? Or let's do it like this here. What is the length here? The length here, which is caused because of the change in the phi, this is equal to r delta phi. Would you agree with this? That's it. So why is the perimeter 2 pi r? Because the perimeter is 2 pi r, because it's equal to the radius times the angle. The angle is 2 pi. That's it. Okay. But if we're not going through the whole perimeter, but we have a very small angle, the arc length here at the edge, or this, or this, or this, it will always be equal to r times delta phi. And we can also write this one r times phi, but we write delta phi just to denote that this is very small angle. That's good. So it looks like here we need to add an r. Okay, so it will be a function of r. That's good. With all this little discussion and try to make this one as intuitive as possible, it looks like we need to write the delta m in cylindrical coordinate system as a vector. This should be AR times AR, wait a second, DR, whatever this is, DR, yes. AR dr plus A phi, R delta phi plus AZ PZ. Okay, now we are good. We are doing meters plus meters should be equal to meters. Now we have to write down the delta V. What is delta V? Delta V, it is an infinitesimal volume, which should be equal to this. This is delta R times delta Z times this R length. Okay. So with this one, we write the following: dr times R delta phi times delta Z. Okay, that's it. So we wrote them correctly. So this was the cylindrical coordinate system. The next coordinate system that we are going to deal with, it is the spherical coordinate system. And in the spherical coordinate system, we're going to have a different geometry. And this one is allow me to erase this part. And in the spherical coordinate system, we're going to have, wait a second, let's see here. We always use as a reference the Cartesian coordinate system. It is a standard basis, okay? This is something which we should always use. Now let's assume we have a spherical coordinate system and we want to describe any point on Earth, okay? Earth is spherical. Now there are some flat earthers around that want to use Cartesian coordinate system to describe the motion of the planes, but let's assume that we are not, we don't strictly believe like them. Let's assume that we have a spherical structure, and the coordinates that we're going to use in spherical coordinate system is going to be r, an angle theta, and an angle phi. R is going to describe how far we are away from the center of the Earth, which is the radius, okay? Which is like 6,000 kilometers. So you drive from here to Germany, it's 2,000 kilometers. If you drive 3 times that, you can go to the center of the Earth. It's not a huge planet, okay? It's really small. So it's 6,000 kilometers, that's the radius r, is this. And then we have an angle theta, which is defined as the angle with respect to the z-axis, okay? And this one will be projected down on the xy like this. And this angle here is called angle phi. So these are the 3 relevant coordinates, okay? So now let's use our intuition. This is r, theta, phi. Then we should include AR, a unit vector along the AR. We should have an A theta, and we should have also an A phi. That's good. Then immediately we should include an infinitesimal small change along the R, an infinitesimal small change along the theta, and an infinitesimal small change along the phi. Okay? So we need these relevant quantities. Okay, and then we can say that, or we have to come up with the relevant delta L. So delta L here, it should be a vector, and it should be composed of what? It should be composed of a change along the R. So let's say, what should be dl? dl should be equal to AR times dr plus A theta, okay, times d theta plus A phi times d phi, okay. Now, all the issue is that it is obvious this is meters, this is radians, this is radians. We have to deal with it. So how can we deal with it? Let's see. First of all, let's try to identify what is AR. AR, it is the direction which points to an increase in r. So let's say you are on the surface of the Earth and you move higher, okay? You raise a balloon and the coordinates of the balloon, it will change by an infinitesimal distance. In what direction? Here. This is AR, okay? Then we are on the surface of the Earth, but we move in the direction of south, okay? With a reference to the North Pole, which means that we can increase the angle theta to theta plus d theta. So we come somewhere here. Okay? So if we're coming this way, that means that a theta is right here. Okay? But what is this length? This length along, so if someone moves, let's say, from Shkodra to Vlora, they are changing the angle theta with respect to the North Pole, okay? So you have a small angle, you are in Shkodra right here, then you travel downward or southward to Vlora, then you're changing this angle. So what is the distance from Shkodra to Vlora? That distance is equal to the radius of the Earth times the change in the angle. The radius of the Earth is r, okay? So we need to include this here. And then, but now let's assume for a moment that we want to go from Vlora to Korcha. Okay, so if you want to go from Vlora to Korcha, we can preserve the, what is the name? The same angle theta. So they both extend. So let's say they both extend from the same angle theta, but we are changing the relative distance from the zero meridian. Zero meridian, it is the meridian which passes through Greenwich in England. So how can we describe this one? We can describe this by a change in angle phi. Okay, so our motion from Vlora to Korcha, it corresponds to a change in delta phi. But how can we represent the distance in meters whenever we change the angle phi? How can this be described? We can have a look at what is the length of this vector. Now, the length of this vector here, the projection down here, it is equal to r, let's not forget this was r sine theta. Okay, so this is the length here, r sine theta. And then what is the distance here? The distance here, it is equal to, let me write this one here, the distance in the xy plane, this is equal to r sine theta d phi. Okay, so here we should include r sine theta d phi. So apparently we were able to write down in spherical coordinate system the differential length. Okay, so if this is the differential length, then we should be able also to write, so for the differential length we can write here that this is equal to AR, this is capital R, dr plus A theta, R d theta, plus A phi, R sine theta d phi. Okay. And the next tricky part, not very tricky, is the infinitesimally small volume element. And this is going to be equal to the first component, this is dr. The next component is r d theta. The next component is r sine theta d phi. That's it. Okay. Traditionally, you might see, so these are all the relevant units. We should also include this. Any vector A is always equal to AR times the projection along the AR plus A theta, the projection along the A theta, plus A phi times the projection along the A phi. This volume you might often see in a correct way, r squared sine theta dr d theta d5. Okay, so these are all correct, but we just wrote it this way to make it clear that we have here meters times meters times meters. They would be meter cube, the complete volume. Okay. Any question for what we did so far? If you like, we can give a short break. Any question you have? Okay, let's